This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. Today we're going to do a Cosmic Queries grab bag edition. So Chuck, what does that even mean?
Well, you know what it means. It means that anything that people want to know, we just throw it in a bag and they get a chance to do it. We used to call it galactic gumbo. That don't show.
Gumbo. I haven't had gumbo in a while, but last I had it, yeah, it did kind of have pretty much everything in it.
Yeah, man.
Whatever might have been left in the fridge overnight. But okay, well, let's do it. You got him.
Yep, we got the questions
nice,
right
my
here.
Co-host, yes.
Thank you. So let's
Bring
jump
it on,
right
Chuck.
into it. Let's go to Chris Hampton, who says, easy name here, Chuck. Hey, thanks, Chris. What the hell? I should really read these before the show. Thanks, Chris. Anyway, do you think future scientists, Neil, will look back at our particle colliders and think that they were somewhat barbaric, i.e. smash, 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 which would also imply that they found a better way to observe particles and parts of atoms while they're still intact?
Wow.
What do you think is better?
I like that question.
Yeah,
that's
it's really
that's
nice,
a very
nice job, Chris.
Peace-loving question.
It is.
Yeah, because atom smashers and particle accelerators, they're entirely designed to smash particles. Now, I don't think particles have feelings, so to be worried about them,
Right.
and to think that we're committing violence upon them,
Right.
So here's how to think about it.
Yeah,
If
rest easy, you little particle pacifist.
particle pacifist. If you smashed a particle and then it was destroyed, and it would never, then okay. But when you smash a particle, what you're doing is you're putting energy into the system, empowering it to make other particles.
Ooh.
So atom smashers, particle accelerators, they're means of infusing a system with high levels of energy to see what pops out the other side, because some particles exist only under those conditions. So what you'd have to say is there a way to observe those conditions without being barbaric to arrive at them? Yes, there is. You know what that would be? Go back to the Big Bang.
Ah.
Okay, there you go with your microscope or with your telescope. Go back to the Big Bang, because those are the conditions we are trying to duplicate in the laboratory. The conditions of density and temperature and pressure. These are the conditions of the Big Bang, and this is what started the field of astroparticle physics. Astroparticle physics, it deals with what happened in the early universe when the universe was small and very hot, and you couldn't have matter as we know it, physical objects. Everything was a particle soup, seething back and forth between energy and matter. And this is what we're trying to create in the laboratory. So these laboratories are actually portals back to the origin of time itself.
Look at that. So basically, they're giant replicators is what they're doing.
Exactly.
Right.
And really, he shouldn't have to be. We're not going to one day find out that particles have feelings. I'm pretty sure about that.
Yeah,
one.
exactly.
Yeah.
No need to have a protest for particles. No justice, no peace. Yeah, we don't. It's going to be all right.
All right, keep it
Very
coming.
cool. All right, let's keep going here. Walquira Fontanez. There you go. I think that's it.
That's it. No matter what, that's it.
It is what it is now. That's what it is now.
Whatever it should be, that's what it is.
That's what it is. Okay. So Walquira says, "Hello, my people. This is Walquira from Georgia, originally from the Bronx. Neil,
Bronx in the house.
There you go. If gravity pulls everything down, then how do clouds defy gravity, and how do clouds stay up?"
Oh, I love that.
Yeah, there you
I
go.
love that. So let me ask a different question that's exactly the same.
Okay.
If gravity pulls everything down, why do helium balloons go up?
Oh, there you go.
So you can ask the question, what does a helium balloon weigh? What does a cloud weigh?
Right.
Does it have negative weight? Do you have to take the scale and put it upside down above it and have it press upwards? Does it have negative weight?
Right.
Okay, that's the question. It's the same question. All right.
Yeah, and it's weight relative to something.
Right? Exactly. So So we, as physical objects called humans, are so much denser than air.
Mm-hmm. Yeah, and you mean that as in a physical sense,
Yeah.
because the other part is true too.
The other kind of dense.
The other kind of dense is also true.
I don't know. When did dense become like you can't learn anything? Dense to me means you have a lot of information in there. There's a density of enlightenment.
See, and that it lets you know who you are, okay? Because you look at dense as a good thing, as in a great deal of information compacted.
Pack it in.
Right.
Pack it in.
And whereas dense as in thick-headed, it's about getting it in there.
So
the density,
barrier.
the density is the barrier. The density of the barrier. You're a thick-headed dolt.
Okay, so it's a thick skull.
It's a thick skull, right?
Don't implicate the whole head here. It's okay. I swear to you, I did not know that.
Yeah.
Okay.
Yeah.
The density of the barrier of entry of information into your mind. All
There
right.
you go.
So you can ask so we are so much denser, physically denser than air. We don't think about how much less we weigh in air.
Right.
Air has a buoyant force that makes you weigh a little bit less, but we don't care about it. We don't even think about it. How about water? Okay, we are almost the same density as water.
Mm-hmm.
So some people float,
Right.
and those who sink, they don't sink very fast.
Right.
So how much do you weigh in water? Well, if you're floating, do you weigh 0? So what's happening here is everything has weight unless you're floating in something.
Mm-hmm.
Okay? So the helium balloon is lighter than air. If you started evacuating all the air of the Earth, then all the helium balloons, however many are still up there, the Chinese balloon, whatever balloon is up there, it will come to Earth. And then you can stick a scale under it and figure out how much it actually weighs with no buoyant force assisting it. Now you pour air back into our atmosphere, and things lighter than air will float above it, but that doesn't mean they're weightless.
Look at that.
Yeah.
That's awesome. And by the way, there's a lot of videos on social media right now circulating that speak to this, questioning gravity because of things that float and the fact that there are things that are on parts of the Earth that they say are upside down. So it's keeping you upside down, but yet at the same time, this same so-called supposed force is allowing these other things to float around. So
okay, so this is a case of a person who thinks they know enough about a subject to believe they're right, but they don't know enough about the subject to know that they're wrong.
there you go. Look at that.
In all the lands down under, that's because like civilization and so the dominant forces of cultures have all been like in the northern hemisphere, right?
Right.
So we have northern hemisphere bias on southern hemisphere resonance, and we say that they're upside down. And even any of us, if we saw a map with south up, we would say that's upside down. And look how deep that bias is, because space don't give a shit.
And
Space-
that's what I was
space
about to
don't
say.
care.
In the blackness of space, when you're floating in a void, right? Is there really any up or down?
Right. No, it's no up or down. Correct.
Right.
Correct. And so, you can point to places that locally will have an up or down where they are.
Okay.
But where you are, no. So up or down is relative.
There you go.
It's relative to where the center of gravity is of your closest object. So anyhow, all I'm saying is if you're floating, it's because there's a buoyant force. That's all. And I once did this calculation for a 150-pound person. What would that be in kilos? That would be, something like 75 kilos. Okay. It's 2.2 pounds per kilo. All right.
per kilo.
So that person, there's a few, it's a measurable amount, but no one cares.
Right.
Is it 100 grams less because of the buoyant force of air? Like I said, we don't typically think about that because it doesn't really matter to us. That's all.
Okay.
All right.
There you go.
Next one.
Fantastic. Let's move on to Michael Ranger. Cool name, Michael Ranger. Is particle a placeholder word for things that are so small we don't know what they are yet.
Is particle a placeholder? Yes, but only for one particle. The electron. Every other particle, every other particle we play with in the laboratory, every other particle that we control and play with has a measured size.
Interesting.
We can give the dimensions of it. An electron, we have never measured how big an electron is. And as far as we know, it's infinitesimally small. This is a profound point of mystery in particle physics. We don't dwell on it because we can still invoke it. We still make current in electricity. We can still do all manner of things with an electron, this thing we call an electron. But it is a spot in space-time that we have never measured. We measure its charge. That's it. And its mass. We can measure its mass, but have we ever seen it? No.
Mass is not size. Right.
It's not size. We've never
mass
seen it.
Mass is not size. Wow.
Yeah.
I just learned something. I did not know this.
You didn't know that about electrons?
I did not know this about electrons.
I have an entire video course with the teaching company, which they changed their name to the Great Courses. What I do in each lecture is I take you to the frontier of our ignorance, and then I just drop you there. And I say, here it is.
Nice.
Peer out, and your guess is as good as mine. Okay,
I like it.
What's going on out there? So
I like it.
I take the viewer to the edge of the unknown in astronomy and physics. It's in the Great Courses series. You check it out if you're interested. In there, I talk about the fact that we have no idea how big an electron is.
That is fascinating. I mean, wow.
Now, neutrinos are pretty elusive as well, and we do manipulate them. And I don't know the latest on those and what size we have ascribed them. Maybe they're equally as intractable in our ability to measure their dimensions. But we do know the size of protons, and they're composed of quarks, three quarks, protons and neutrons. And how big is a quark? I don't know what our latest thinking is on that. But the fun one is electrons, because we've all heard of electrons. We
all know what they are.
We all know what they are.
They're the satellites of the nucleus.
Yeah, that's right.
The nucleus.
Well, they quote orbit the nucleus.
Right.
But we didn't want to use the word orbit because that applies to planets. And so we invented a new word, orbital. So they have orbitals, right? Just to put a little distance between it and astronomy. Yeah.
Wow, look at that. Dude, what a great little question you had there, Michael Ranger. Thanks for that, man. Yeah. Okay. All right, here we go. This is Michelle Stargirl. Watch out. Watch out now. It's Michelle Stargirl.
Stargirl. That's her name?
That's
the handle.
what she wrote.
That's what she wrote.
That's what she wrote.
That's the handle.
I'm not going to judge her because that's what she wrote. She goes, greetings. This is Michelle from NYC. Now that the James Webb Space Telescope has seen mature galaxies not long after the Big Bang that under current knowledge shouldn't exist, could these galaxies possibly be a window into another universe?
Ooh, I like that.
Oh, what a lovely conjecture.
Like that. Thank you, Stargirl.
Stargirl.
So, when I was a kid, one of my favorite cartoons was Astro Boy.
Oh, God.
Do you remember Astro Boy?
They brought Astro Boy back, man?
They did. I didn't know that.
Yeah. Astro Boy bombs away on a mission today. Rocket high to the sky. Okay, anyway.
So let's back up. So after the Big Bang, where there was this particles matter soup, everything was too hot to make stars. And so, but then there's a point where things cooled so that the universe became, because the universe was glowing back then, it cooled and became transparent, but it still was not ready to make stars. So it would have to wait. I forgot how long, but long enough so that we have a word for this era, and it's called the Dark Ages, where there's no stars, no galaxies.
Right.
James Webb Space Telescope is exquisitely tuned to observe the birth of galaxies. So we turn on the telescope, look back to this era, and we find red-blooded galaxies doing the backstroke in the Dark Ages.
Wow.
So that freaks us all out because it's like, okay, who ordered that?
Right.
And nobody ordered that, okay? So either our entire understanding of the Big Bang and expansion and cooling of the universe is wrong, or these are varieties of galaxies that we haven't seen before. And we're mistakenly putting them in a place where an ordinary galaxy would have been with those same properties. But could there be a different kind of galaxy with those same properties that is otherwise unfamiliar to us? This happens all the time, by the way. So you say, oh, I know who you are because you're standing there and you're doing X, Y, Z. Because I'm using information that I think should describe fully who you are. Turns out you're not that. You're something completely different. So all my understanding of you being there is wrong. Is completely wrong. So if you're a betting person, I would not bet against the Big Bang.
Exactly. I see what you're saying. So it's kind of basically like when you're looking back, because you're looking back in time, but you're looking back in time through different wavelengths, is what you're saying.
Yeah, correct. And we have our catalogs of everything that we understand.
Right.
And we're looking to a place we've never looked before in wavelengths that we never received from that part of the universe. And we see objects, hey, these look like our galaxies that don't belong there. Maybe they're not our galaxies.
Maybe they're not our galaxies.
Okay, maybe there's nothing in this catalog that we have created of everything nearby to us.
Right.
Maybe there's a whole new early universe catalog
completely
that we have to form.
Yeah. It's like looking at an ultrasound and you see a baby, but the baby is like watching TV and smoking a cigar, right? You're like, hey, something's wrong with this. Something's up, but it doesn't necessarily mean that it's not a baby in there. You know, it's
right. Yes, I don't know what the hell that would be, but if you...
dude, that's so great. All right, well,
let's close this out. This first segment, and when we come back, more Cosmic Queries grab bag when StarTalk returns. We're back. Cosmic Queries grab bag. These are fun. I like grab bags. Chuck?
Yeah, exactly.
I got Chuck nice with me. Oh, Chuck, I have something to add to that question, how much does a cloud weigh?
Okay.
I want to add something to that.
All right.
So generally, if you look up whales in a book or on a wiki page, it'll say how much they weigh. Right? Okay. And there's a lot. They're the heaviest animals that ever existed.
Mm-hmm.
But is it really fair to say how much they weigh? Because you know what you're doing? You're taking them out of the water and putting them on land and measuring them on dry land immersed in air.
You big blubbery fat butt.
Stop. Tell that to its face.
Exactly.
So the point is, the whale doesn't live on land.
Right.
It lives in the water. So what matters here is not the air buoyancy it gets, which would be irrelevant as it is for us. What matters is the water buoyancy.
Right.
So in water, a whale weighs 0. Okay? It can move up and down freely the way a perfectly neutrally buoyant balloon could move up and down freely in our air. So to a whale weighs nothing.
Wow. That's kind of cool.
Yeah, because in the medium, it weighs nothing.
Right. There you go. Yeah.
It is.
That's very cool.
Okay.
All right. Here we go. Let's keep moving on with...
Keep it moving. Keep on moving.
We're going to keep it moving with... This is Rebecca. I'm going to say Fuchs.
Okay.
Yeah. Spelled could be a bunch of different things, but I'm going to go with Fuchs.
Fine.
All right. She says, hello, Dr. Tyson, Lord Nice. Rebecca from Connecticut here. Could you please explain, in the simplest terms possible, please, why do we think that space and time are emergent and not fundamental? I don't know what that means, Neil. Oh, I don't even know what she means by that.
So there's been some murmurs about it being the consequence. Well, so I can tell you the little bit that I know. Okay. Actually, I think that question might have come in when we had Stefan Alexander here, who was a sort of cosmologist, particle physicist dude. And maybe he would have been better equipped to answer that. But let me tell you what I just learned in a conversation with Brian Greene, who's right up the street from us in Columbia University.
Our buddy Brian.
The author of the best-selling book, The Elegant Universe, and he followed it up with The Fabric of the Cosmos. Anyhow, here's what he told me, and it's blew my mind, all right? So, you got to hang with me for this.
Okay.
So quantum physics tells us that there's no such thing as empty space.
Okay.
That in empty space, where you would classically say there's zero energy because there's nothing there, quantum physics says, there's always a chance of there being some energy everywhere. Okay? And this is called the vacuum energy of the universe. This is what it's called. Okay. So how is this manifested? So if you run through the quantum physics equations, you get particles out of that energy popping into existence, matter-antimatter particle pairs that then rejoin and make energy again. Okay, so energy is coming and going with particles, and it's a seething soup within the vacuum of space. Okay, and these are called virtual particles. So no one denies that they're there, even though we've never measured them. There's a very natural prediction of quantum physics, and what quantum physics, everything else quantum physics had predicted, has turned out to be correct.
Right.
So we're sticking with this explanation. Now, it turns out, these particle pairs, since they were created together, know about each other. They know about each other in a quantum entanglement sort of way.
Okay.
Well, if they know about each other because they're quantum entangled, and quantum entanglement means if something happens to one particle over here, the other one knows about it instantly. And the only way we can think about that is if there's some kind of wormhole between the two of them where it doesn't have to then travel through the physicality of space. Some kind of wormhole, because then you can get to two places instantly without, quote, violating the speed of light rule. So here's what he told me, that there's some emergent thinking that suggests that the very fabric of spacetime is the network of these wormholes created by the seething soup of virtual particles. So that those wormholes are themselves the fabric of the universe. They are weaving together the fabric of the universe.
Wow.
And that blew my mind. So because we speak of the fabric as distorting, and it's sort of metaphor, right? And, but is it literal? Is it a literal thing that could be true? So there's that. Okay, so now about time, what I do know is that we measure time by things that repeat. Okay?
Right. Cycles.
If nothing repeats, you can maybe know what happened before something or after something, but you wouldn't be able to measure the time between it. So I don't know about time as being emergent relative to what I just learned from Brian Greene, that the very fabric of space-time might itself be emergent and a property of the vacuum. So I lost a few nights of sleep on that one.
I don't blame you. Jeez, I'm losing just brain cells listening to it. That is freaking trippy.
And so, Chuck, this word emergence, of course, has its own meaning in biology, in biological circles, in evolution.
Absolutely.
Right? Because you could look at a bird like pecking away on the ground, and you can study every atom and molecule of that bird, and you probably would not know that a group of birds will flock together by analyzing a single bird.
Right.
So that flocking is sort of an emergent feature of a group of birds that you would never learn by studying one bird. We don't, as far as we can tell, you wouldn't learn it. So emergent property, maybe consciousness is emergent.
Exactly.
Which they're worried about AI. You keep programming up AI, bada bing.
If you get enough data points coming together with enough computing power, then all of a sudden, it's not that you made it intelligent enough to become sentient. It just becomes that because of those things.
Way. Right. And I just saw the preview again for that movie Megan.
Oh my God, I love that movie.
Oh no, I can't see the movie after that preview. That's the
oh God, I love that movie so much.
So that's an emergence. But here in the universe, the emergent would be something that was not there from the beginning. Right? It would just show up later because something else happened. So this is how we're using the term in physics, which is a bit different from how it's been commonly used in biology. That's all.
Cool, man.
Yeah, all right.
Well, Rebecca, what a great question. Look at
thank
you.
Thank
you. That
you.
was very cool. All right, let's go on to Catherine B here. And Catherine B says, Good day, all. My name is Catherine, and I'm from a small, insignificant town near Ottawa, Canada. Don't sell yourself short there,
I know,
Cat.
right? Let us be the judge of
Yeah,
whether
we
it's
can tell you.
insignificant.
We can tell you you don't matter. You don't have to lead with that.
Let other people tell you. It's,
Yeah, let other people put you down. That's how you know you're Canada and not American.
right?
Because we other people around the world got to put us down. We're like, we're number one. All right. She says, I have a question that I have not been able to find the answer to, and I know you can answer it, Neil, or at least you'll have a theory about it. If time speeds as we leave Earth's gravity and slows with velocity, how will astronauts traveling to Mars be affected once they leave Earth's gravity? Does it no longer slow, so they will only be impacted by the speeding up of time because of their velocity? If that's so, how long will a 3-year Earth journey be for them? I hope I'm making sense right now.
Completely. So
there you go.
So this is a combination of a bunch of things. We know that the closer you get to a source of gravity, the slower time ticks for you.
Right.
The farther away, the faster it ticks.
Right.
The faster you move, the slower time ticks for you.
Right.
So if you are not only moving farther away from Earth's gravity, which would speed up time, but now you are traveling fast, that would slow down time. You got to run the equations and see which equations win.
Right. Which is greater? Which is a greater pull?
Which is a greater, and I can't do that in my head. I could do that on paper. I can do it. But here's one I did do already, and that's for GPS satellites.
Okay.
So GPS satellites orbit the Earth at very high speeds. So relative to us, their time is slowing down, okay? If you only factor in their high speeds. But they're also much farther away from Earth's surface than we are.
Right.
So the time is speeding up. And the speed up time is about twice what the slowdown time is.
Mm-hmm.
So the speeding up wins.
Gotcha.
The speeding up of the time wins against the slowing down of the
down time
for its orbital speed.
Right.
Which means the GPS satellites do not keep the same time we do.
Right.
And they have to be pre-corrected before you get the time signal from your phone company.
Wow.
Yeah.
So these factors are all in working in either conjunction or against one another at all times.
At all times.
At all times.
And it's cumulative. It's cumulative. So
okay.
if you're on a mission for 3, by the way, it's very tiny. It's cumulative but tiny. So
okay.
You want to know how much younger or older is your twin astronaut sibling who went to Mars? It would be fractions of a second.
Gotcha.
Yeah.
There you go.
Just off the top of my head.
Wow. It's still fascinating because it's not a perception of time that
correct.
is speeding up
it is
or
the
slowing
actual
down.
Speeding
it
up
is
of time.
actual time itself.
Yes, timekeeping devices, your heartbeat, your brain thoughts, everything.
Everything.
Slows down. Mm-hmm.
So crazy.
Mm-hmm.
Yo, all right. Hey, Catherine B., thanks for that. That's very cool. Look forward to some more information forthcoming about your trip to Mars, Catherine, because I know that's why you asked.
You got a plan.
I know. You're like,
got a plan.
I'm from nowhere, Ottawa, but I'm going to Mars. So how about that?
Okay.
Let's move on to... Okay, man, you just messing with me. This is Ketty Kukunasvili. Mm-hmm.
Don't pretend like you knew that. It's that's a good act there.
Yeah.
Okay.
Ketty Kukunasvili.
Yeah.
Okay.
All right. That sounds like it could be it.
Kukunasvili. Okay.
All right. Go ahead.
Hey, Neil. Hey, Chuck. I'm new to Patreon, but a long-standing fan of StarTalk. I have a very basic question. Why is string theory so unprovable? And if so, why are we still trying to prove it?
You know, every time I see Brian Greene, I slap him upside the head and say, Brian, why haven't you string theorists solved this problem yet? And his answer is, well, it's a very hard problem. Well, so was general relativity, and Einstein did it all by himself, and he took 10 years, which was a long time for an Einstein brain, but he solved it. And here all y'all That's the plural of y'all.
Right.
It's all y'all.
All y'all.
Okay, here's all y'all strength theorists. There's dozens of them. Probably not much more than that, but I would say dozens of them in the world. Been working on it for 40 years. And so why don't you all, so I said, why don't you just confess to yourselves you are collectively too stupid to figure it out.
Oh,
Or I said this to his face. Or that or that it's not the problem that you should be solving, and the actual solution is something else that nobody's thought of yet.
ooh.
Yeah, I was in his face.
Oh my goodness. Yo, that's hardcore, bro.
It was. Now I'm bigger than him, so I knew I could.
I was gonna say you gotta call into question the veracity of his entire life's work. That's a little rough, man.
It's a little rough. It's a little rough. Yeah, I did it to be, of course, purposefully antagonistic.
Of course you're joking. Right.
But it was, how long are you going to say the problem is just hard rather than we are barking up the wrong tree?
Ooh.
So that's kind of how I think about it. Plus, it assumes that there can be one coherent theoretical understanding of all phenomena in the universe. It assumes that. And you're putting your philosophical mission statement on the universe that you're investigating. And the history of that exercise has never proven to be successful. I'll give an example. Copernicus says, I think the sun is in the middle of the universe and not Earth. And so let me create a sun-centered universe. So he does it. And he puts the sun in the middle, and Mercury, the orbits of Mercury, Venus, Mars, Jupiter, Saturn. The asteroid belt wasn't discovered yet. But on out. He does this. Okay. Do you realize it was still wrong? Because he assumed that the universe is God made the universe is perfect because God is perfect. So clearly God made orbits that are perfect circles because a circle is a perfect shape.
Circles. Right.
So that was a theoretical expectation placed upon his ideas about how the universe is put together.
Wow.
And it was just wrong. The orbits are squashed circles, and they're all squashed differently. And the most squashed circle among objects known as planets, or formerly known as planets, is Pluto. Pluto's orbit is so squashed it crosses the orbit of Neptune.
Right.
This is hardly the handiwork of someone who really cares about perfect circles, all right? So I just like to take a step back and stay open to the possibility that there's a whole other idea that could supplant everything they're doing that wouldn't take 30 people 40 years to try to figure it out, because that's a lot of brain power going in there. In all fairness to them, they made certain progress with their string theory in using it to interpret things that we now understand more deeply. Okay, so that works. And by the way, how close are we to proving it experimentally? Some predictions are forever in the future will never, no. Okay?
No matter what.
But
some of it is interdimensional.
That's the way you, yeah, I'm going to go there too. You're holding your chin like you're contemplating. Interdimensional, yeah, a higher dimension. I got this one. All right. The point is, you can have a hypothesis that is untestable in its core, but if the hypothesis is true, some other things might be true that you can then test.
All right.
So you can test the edges of it, all right? And that can still make progress on the thing that you're waiting to test if you can't do it today.
I got you. That makes perfect sense. And what you're saying is they're not even close to that. Damn. That's rough, man.
Yeah, so here's what Einstein said. Einstein said he has something called the equivalence principle, deep and profound statement that the mass that gravity sees when it pulls on you is identically equal to the mass that a force sees when it accelerates it through space.
Ooh.
Okay, these two masses, there's no reason in heaven and earth why these two masses have to be the same.
Right.
But they sort of seem to be the same, and Einstein said, let us declare them to be the same. And if they are the same, here's something that would be true. And what is that? If I'm in an elevator and you cut the cable and I let go of a ball,
right,
I will fall, the elevator's falling, the ball is falling, and it'll stay stationary in front of my face.
Right. You'll be falling at the same rate. And then also Einstein will have to face murder charges.
What? At the end of
that experiment.
It's only if he cut the cable.
Yeah, oh, that's true. He's probably too smart to cut the cables himself, to be honest, right?
Okay, so the point there is I am in free fall, okay?
Right.
Fine. But if I had, so I'm 0G, but if I'm standing on Earth, watch this. I'm standing on Earth and I let go of the ball, it falls. I'm in 1G. Okay, so now watch. Now I have rockets on the back of your ship, and I accelerate you through the universe at 1G. And you holding a ball, you let go of the ball, it'll fall down to the ground. You cannot distinguish whether you were in a rocket accelerating through empty space or standing on a planet under that same 1G force.
That is such a elegant little thought experiment.
Elegant and profound. And you could do these experiments. It's a thought experiment. You could do the experiment.
You can actually do it.
Right.
Yeah.
On the edges.
On a train, or I think that's what they did. Yeah. That's so cool.
Okay. Got to take another break. When we come back, more Cosmic Queries, the Grab Bag Edition. We're back. StarTalk Cosmic Queries, Grab Bag Edition. So, Chuck, why did we stop calling it Galactic Gumbo? Because that was fun.
I think maybe people got tired of me imitating
Paul Prudhomme.
Yeah, Paul Prudhomme. That old Galactic Gumbo.
Wait, is he the one that spoke like that?
I don't know if it was him. I just know that guy was on PBS and he was amazing because he'd be like, now, here what we're going to do here. Then we're going to bring that on there and put that. And
whoever that guy was, that's the guy. Okay.
And then we're going to add some cayenne pepper. That was amazing, that dude. He was awesome.
So we got some more questions. Bring it on.
All right, here we go. This is Captain James Riley.
Okay.
Captain Riley says, if a photon is a particle,
which it is,
can't it just sit still? Why does it always have to be moving at the speed of light?
Oh.
Wow, look at that.
Okay, so here's what we have concluded. And this might sound like a cop-out answer.
Okay.
Objects that have mass can never attain the speed of light.
Oh.
And objects that do not have mass only exist at the speed of light. That is the hand we're dealt in this universe.
Wow, so it's a massless particle that ceases to exist when it stops traveling at the speed of light.
Well, it can't not.
It can't not.
Right, yeah, right. So what will happen is,
so it has to hit something.
Exactly. So if the energy of that particle is going to become matter,
right,
then the matter has to be moving slower than the speed of light. But the energy budget remames the same. We're fine on the energy budget.
Exactly, because you got a little exchange going on there.
Exchange going on. V equals MC squared. Yeah. So I'm not answering it with a why. I'm just declaring that is the universe we live in. Now, you want to hear something profound?
Okay.
I think. Okay. This is profound. You may know that time slows down as you go faster and faster and stops at the speed of light.
Exactly.
Okay? Okay. Well, neutrinos, there was something called the solar neutrino problem, where everything we understood about thermonuclear fusion in the core of the sun told us how many neutrinos it should be making. We built detectors on Earth, and we were detecting only a fraction of the predicted neutrinos.
Okay.
This went on for decades. And people say, maybe we don't understand fusion. But it worked out. We're getting the energy budget for the sun. That seemed to work. Maybe there's something wrong with the detector. No, we got the detector thing. So what's going on? Okay. Here's what we found. Well, plus we didn't quite know how fast do neutrinos move. Could they be moving the speed of light? Okay, we don't know. Here's what we found. There's more than one species of neutrino.
Ooh.
And the neutrinos emitted by the sun change species en route to Earth. So the detectors we built were detected to find only the kind of neutrinos that the sun made, not the kind of neutrinos that ended up landing and arriving here on Earth. It'd be as though I tossed you a basketball,
right,
and you received a football.
Look at that.
But you set up detectors only for basketballs.
Right.
Okay, so now watch. Wait. So that meant it's called neutrino, there's a term for it in physics. But basically, it decays into another species. Okay?
Gotcha.
Okay. Wait a minute. If it knows to do that after a certain amount of time, then it can't be traveling at the speed of light. Because if it was at the speed of light, it would have no concept of time and would not know when to change species.
Transition.
Exactly.
It could not know because traveling at the speed of light means that it can only exist as it is while it's traveling at the speed of light.
Correct. Because there's no time clock to tell it to do anything else.
There's no time to tell it what to do.
Correct.
Yeah. It's
so
like,
in one swell foop, we learned that we're looking for the wrong neutrino, and the neutrino does not travel at the speed of light. It travels very close,
but not the same.
But not the same.
That is fascinating.
Yes, this is science, dude. This is crazy, fun, interesting phenomenon.
It really is.
Yeah.
I just love that the neutrino is like Tom Cruise in the Mission Impossible.
Oh.
It leaves the sun and then it gets to Earth and it's just like
pulls
its face off like it was me all along.
You can't detect me. I don't. So you got another question.
All right. Wow, that was really good stuff. Thank you.
By the way,
Captain James Riley.
our crack team of researchers behind the camera reminded me of the simple physics term. So when neutrinos change species, they're called neutrino oscillations, we call them.
Neutrino oscillations. Yeah. That is so cool.
But it will only know to oscillate from one species to another if there's an internal clock. And it can only have an internal clock if it's going slower than the speed of light. It's that simple.
All right, here we go. This is Walker Folland. And Walker says, "Gentlemen, this is Walker from West Branch, Michigan." I don't know why I think he sounds like that, but he goes, "If two objects travel parallel on a sphere, three-dimensional sphere, they will eventually converge at a point.
Yes.
If we extrapolate that the fourth dimension, does that roughly explain behavior of gravity in our universe?" So if we extrapolate that to the fourth dimension, does that roughly explain the behavior of gravity in our universe?
Yeah, so for us, the fourth dimension is time. And so I'm not quite getting where that would land. But let me just remind people that we learned in grade school, perhaps, certainly by middle school, that parallel lines never intersect. That's only if the space in which they're embedded is completely flat.
Right.
But if it's curved, like on a surface, parallel lines, and a line is very rigidly defined as if you cut through that line, that cut will go through the center of your sphere, okay? That assures you that that's a proper line, a geodesic it's called, or great circle route if you're taking an airplane. Okay, so two lines that are parallel will ultimately intersect in two places on a sphere, okay? Which is which is interesting because we refer colloquially to lines of latitude as parallels. Lines of latitude do not intersect. And we're borrowing the concept of non-intersecting lines being parallel and applying it to the surface of the Earth and calling latitude lines parallel. But they're not parallel because they're not authentic lines. There's only one authentic latitude line in the world. And what line is that?
The equator.
The equator. Because you can cut through the equator,
Cut through
that goes through the
and
center
goes
of
through
the
the
Earth.
center of the Earth.
All the other cuts do not go through the center. They're not legitimate lines. And that's why airplanes don't go along latitude lines, because it's not the shortest distance between 2 points.
Wow.
Yeah, you ever see the airplane trajectories? It's always, well, why are you looping up like that?
Right.
Let's just go along this straight line here on your Mercator map, which completely distorts how you got to get from one place to another.
Wow. Look at that.
Yeah.
That's very cool.
Yeah. So, but I don't think I answered the question. What was the question?
Well, because he's saying that if we were to extrapolate that out to the fourth dimension, which is time, would that explain gravity in our universe?
Yeah, I don't feel that. I don't feel. What I do know is that as you go back in time, the universe was smaller. So if you imagine our universe as the surface of a sphere that is expanding, we're all just on a surface, okay? So I lost a dimension just for the sake of this explanation. So if you go back in time, the universe was smaller, and then smaller and smaller. So you can follow a time arc backwards, and all time arcs will meet at the center of the balloon.
Okay.
So if you ask on the surface of a balloon, where's the center? I say it is nowhere on this balloon. The center of our universe exists in time 14 billion years ago. Let's find that center. And now you go back in time as the balloon shrinks, and there it is, infinitesimally small. That is the center of everything. That is the center of the universe.
Wow, that's fascinating.
So time has a center in a way.
Right. Exactly.
Yes,
right.
yes.
Right. Yeah.
Dude,
yeah.
that's all the time. That was a mind-blowing. I'm
That
exhausted.
oh man,
Damn.
these people came with it today,
They
boy.
came out of the bushes for that one.
Yeah, it really did. It
Yeah.
was good stuff.
Yeah. All right. Thanks everyone for those questions. Great to have a new Patreon member coming in on the Q&A. And all right. And by the way, these are all Patreon members, correct?
All Patreon members. Yeah.
This has been StarTalk Cosmic Queries, the grab bag edition. Chuck, always great to have you there.
Always a pleasure.
I'm Neil deGrasse Tyson, as always, wishing you to keep looking up.